Assalamu alaikum students. So welcome to the lecture 8 of this FM2 course, and in this lecture we will be talking about the drag force. We are already discussing the flow around the immersed bodies, the bodies that are immersed around in a fluid, and what if that body is experiencing certain amount of force, and whenever a body is immersed in a fluid and a flow is passing through it, then it experiences a kind of a drag force. And in this lecture we will be talking about the drag force, the types of the drag force, and the different uh, characteristics of a body shape, the characteristics of the flow that influence this drag force. So let's talk about the drag force, its types, and the characteristics of the flow and the geometry that affects this force. Drag force, this is the formula for drag force, and it is in terms of the drag coefficient. This is the drag coefficient, and it is equal to the drag force divided by half density, velocity square, and area. Area can be both planar area, it can be planar area, or it can be the frontal area. We already discussed the planar and the frontal area. Planar area, if we are looking from the top at our object that is immersed in a fluid, and frontal area if we are looking at if we are taking the front view, or we are looking at it in the direction parallel to the flow, and in this case we'll be looking at it normal to the flow or from the top. So these are the areas. We will discuss it a little bit more when we talk about the shape dependency of the drag force, and this is represented in terms of the drag coefficient. And the drag coefficient is a function of shape, Reynolds number, Mach number, Froude's number, and the relative roughness. And we will be seeing the effect of the shape on the drag force, the effect of the Reynolds number, that what will happen when you change the Reynolds number, the effect of Mach number, Froude's number, and the relative roughness. What will be the effect of these parameters when we change them? What will be the effect on the drag coefficient? And as you remember, we discussed these diagrams, the aerofoils, and we said that when they are immersed in a fluid and when a flow is passing through them, what will happen, that it will experience two types of forces. One will be the force that will be tangential, that will be tangent to this surface, and that will be the shear force. And one will be the force that will be normal to the surface, and that will be the pressure force. So drag is also classified by the help of these two forces. If we take the shear forces, then we will call that for the friction drag. If we take the pressure forces, then we will talk about pressure drag or form drag. So these are the two forces that influence the classification of the drag force. And in one case, in shear force case, the flow is parallel to the shear force, and in the other case the flow is perpendicular to the force, and in this case this is the pressure. So let's talk about the friction drag first. And friction drag, as we said, is due to the shear stress. This is due to the shear forces that is acting tangential to the surface of the body that is immersed in the fluid. Then it is a function of not only the magnitude of the wall shear stress, but it also depends on the orientation. It also depends on the orientations of the object, and it does not only depend on the magnitude of this force, but it also depends on the orientation. For example, if we take a flat plate like this, and this is our flow, then this flat plate will experience a certain amount of drag force near its surface. But if we take the plate and place it like this, then the friction drag in this case will be minimum, and the whole drag will be the pressure drag that will be normal to this surface. And in this case right here, the pressure drag will be minimum. So in this case right here, the friction drag will be maximum, the pressure drag will be minimum, and in this case the pressure drag will be maximum and the friction drag will be minimum. So that's how the drag force is dependent upon the shape, but also the orientation of the body. So, as we said, if the surface is parallel to the upstream velocity, the entire shear force contributes directly to the drag in this case, as we already discussed that in this case the the free stream velocity that is parallel to the surface. So the entire shear force contributes directly to the drag. And if the surface is perpendicular, just like in this case, then the perpendicular to the upstream velocity, the shear stress contributes nothing to the drag, but the whole drag is caused by the pressure forces. So the friction drag on a flat plate of width B, length L oriented parallel to the upstream flow can be calculated. For example, if this is the flat and the plate, this is the length L and this is the width B of the plate, then what type of area we are talking? We are talking about the plane form area. We are talking about the plane form area in this case, as we already saw in the previous lecture, that for the case of airfoil we will take the plane form area, and in case of a cylinder we will take a, that is the diameter, that is the length. We will take this DL as our area. In this we will take the BL as our area. So this is the frontal area, this is the frontal area, and this is the plane form area which we take with the help of our top view. So the area that is formed in the top view. So for example, if we take a plate that has a length of L and width B, then what will be the drag force? So the drag force will be equal to half rho u square, and this is the area term multiplied by the friction drag coefficient, and the friction drag coefficient can be read from the table. It has a special table in which the friction drag coefficient is represented with respect to the Reynolds number, and that table can be read from here. That is table 9.3, and you can see for different flow conditions, for laminar flow, for transitional flow, for turbulent flow, and for completely turbulent flow, the drag force coefficient is represented in terms of the Reynolds number or in terms of the relative roughness of the surface. So that's how we can use this formula and this table. If we know the density, the velocity, or planar area, then we can actually find out the drag force that is being exerted on the body immersed in a fluid, especially the friction drag force. This is what we are mainly talking about. So now let's see what pressure drag is and discuss it a little bit further. So as we said, that the friction drag is due to the viscous shear forces, and of course by the name you can see that pressure drag will be caused by the pressure forces that are acted normal to the body. So the drag that is directly to the pressure on an object, and it is often referred to as form drag. The pressure drag can also be known as the form drag. And its strong dependency on the shape or form of the object. The pressure drag is also strongly dependent on the shape and the form of the body that we will see in a little while. And if we consider a plate, and if it has a certain area, differential area dA, and this is the flow velocity direction, then the the pressure force will be normal to this plate, as you can see. And we can write that if this is our reference, then this term will be PdA. Then we can write that in terms of d cos theta, like this. That is the pressure force. The drag pressure force can be represented in terms of pressure into area. So it can also be represented in terms of coefficient form. This is the drag pressure coefficient, and it is the same term that we use for the friction drag, but here we can also substitute this drag force with this term right here. So let's do that. We will have this term right here, the pressure drag force will be substituted with this term right here, and we will get now this term for our pressure drag coefficient, and this term right here inside the integral, that P over half rho u square. If you take a certain reference pressure as well, that is known as the pressure coefficient, and it is dimensionless. This is the dimensionless less entity, and that pressure coefficient can be seen right here, that we can also represent the drag coefficient, the pressure drag coefficient in terms of the pressure coefficient like this. So here again the pressure coefficient is equal to this term. As you can see, if we take out these terms right here, we can write them in terms of pressure coefficient. If we take also a certain amount of reference pressure, for example, if the reference pressure is a vacuum, then this pressure will be equal to 0. We will get P divided by half rho u square, and if this is some amount of a pressure, then we will be talking about gauge pressure that will be subtracted from this pressure, and we will take the actual amount of our gauge pressure. So in both cases we will be left with this term right here if we know our reference pressure. So that term right here is equal to the pressure coefficient. So let's discuss this a little bit more, that what will happen if we increase the Reynolds number. For example, this is what we already discussed, that this term right here, this is the pressure coefficient, and is the pressure coefficient will P naught is the reference pressure. So there can be two scenarios, that is let's say if we are going to discuss this pressure drag. So in the first place, let's say that the inertial forces are very large. So what will happen to the pressure drag if the inertial forces are large? So what will happen to the pressure drag coefficient? As you can see, inertial forces are large. So what does that mean? We know that we have a Reynolds number, that is the ratio of inertial forces to the viscous forces. So by large inertial forces, we mean that we have a very large Reynolds number. We will have a very large Reynolds number. So in this case, the drag force, the pressure drag force will be very minimum, but so much so that the drag force will be independent of Reynolds number. It will be independent of the Reynolds number due to the high energy in the fluid particles, because at high Reynolds numbers the fluid particles will have high energy and it will not stick to the surface of the body that is immersed in a fluid. So in that case, the drag coefficient will be independent for high inertial forces in the case of a high inertial forces. The other way around can be if our viscous forces are very large. Say that our low Reynolds number flows. For example, when this term in the denominator is large for our Reynolds number flows, then the pressure drag is inversely dependent on the Reynolds number. Say if we decrease the Reynolds number, then the drag pressure, the coefficient will increase. So these are the two scenarios for this drag pressure coefficient. One is the high Reynolds number flows, where the flow can be turbulent and the particles, the fluid particles have high energy, they will not stick to the surface of the body. And the other scenario is the low Reynolds number flows, where the viscous forces are dominant, and in that case the Reynolds number will come into play, because the fluid particles will have low energy, they will stick to the boundary of the fluid, and in that case we will have a drag pressure, we will have a certain amount of drag due to the pressure forces or due to the friction forces, in that case the shear forces. So these are the two scenarios that we already discussed. We discussed the scenario for low Reynolds number, and we said that in this case the separation, there is a separation bubble because due to the separation phenomena that we already discussed in the boundary layer, and the viscous effects are quite prominent in this case, because this is the low Reynolds number flows. And we will have boundary layer, and we will have a certain amount of the drag coefficient being acted on this blunt body. And then we had another scenario, and that was the high Reynolds number flows that we already discussed in the previous lecture. And you can see that how the viscous effects are reduced. You can see from the gray area that here, this area right here is large. The viscous forces are dominant at low Reynolds number, but in this case Due to the high energy level of the fluid particle, the viscous forces become reduced and the viscosity effects are reduced for high Reynolds number flow. So this is the exact concept behind this phenomena that we discussed, that what will be the drag force for high inertial forces. Inertial forces means that we have high Reynolds number, so the viscous forces will not be dominant, and in that case the drag force will not be dependent upon on the Reynolds number. But for low Reynolds number flows, the drag force will be inversely dependent on the Reynolds number, and if we reduce the Reynolds number, then the drag forces will become more dominant and dominant. So this is the effect of the drag force. Then we talked about that the drag force is a function that is dependent upon the shape of the object, and whenever we take a certain amount, a certain shape, to see how that is dependent upon the drag force, we take an ellipse. We take an ellipse because that ellipse can have two axes. One is the major axis, the other is the minor axis, and it is represented as D, and the other is represented as L. And we take the ratio L by D ratio. This is also called the axis ratio. This is also called the axis ratio. And by changing the axis ratio, we can actually change the shape of the object. So by seeing the shape dependence, we can take this one variable and we can see different shapes by changing the value of L and D. So as you can see from this graph right here, this graph shows the drag coefficient for an ellipse with the characteristic area, either the frontal area, that is in this case, and the plane form area, that is for this case. So the frontal area is this one. If this sphere that here is a certain length, if this also has a certain length, then that will be called B. It has a one axis, that is D, and the other axis, that is L. And here the drag coefficient is plotted with respect to this L by D ratio, the axis ratio. So here, as you can see, the drag force is maximum for this L by D, which is equal to 1. So by L by D, that is equal to 1, means that our body is in the shape of a circle. It is a complete circle. So for that purpose, the drag coefficient will be very high, and here it is for this scenario. For this scenario where the L by D ratio is 0, and L by D ratio will be 0 when this term right here is 0. So that means that this term becomes neglected. So what will happen? This shape will convert into a flat plate. This shape will convert into a flat plate, and all the drag that will be caused due to the pressure forces. So in this scenario, for L by D equal to 0, that will be the flat plate scenario, and for L by D equal to 1, that can be the complete circle scenario. And for both the cases, you can see that how the drag is maximum. The drag is maximum for flat plate. Here the drag force is somewhere around 1.9, and for a complete circle the drag force is right here, that is above around 2.4 something, the drag coefficient value. And as you can see, as we go down, as this ratio, L by D ratio, increases, then the spheroid changes its shape. Actually the length diameter increases, the D diameter decreases, so it becomes more and more streamlined. It becomes more and more streamlined, like it can be at first like this, that is the D diameter. The D parameter is maximum, the length parameter is minimum. So as the length parameter increases, the body becomes more and more streamlined, and it will ultimately experience less drag force, and due to the streamlined shape of the body. So that's how the drag force is dependent upon the shape of the object. And for shape dependency, we take an ellipse, and the ellipse has these two axes which we can change and get different shapes, from a complete flat plate to a complete circle, by just changing these two ratio, the L and D ratio. So that's how we check the shape dependency of drag force by using an ellipse. Now we will see the effect of the drag force with respect to the changing Reynolds number. That what will happen if we change the Reynolds number and see the effect of drag force. In the previous slides we saw the effect of drag force on the shape of the object, and now we will see that if we do not change the shape of the object, keep it constant, so what will be the Reynolds number effect on the drag force or the drag coefficient. In this scenario, we will be using this graph at which we have different drag coefficient values at changing Reynolds number from very low to very high, and we will be explaining each point A, B, C, D, E, that what is happening and why the drag force is changing with the increase in Reynolds number. So the first one is the point A. And at point A, this is a point at very low Reynolds number, and that here the Reynolds number is approximately 10 to the power minus 1 to the 10 to the power 0, and this is called the creeping flow regime. This is the creeping flow regime. Here the Reynolds number is very low. This is called the creeping flow regime, and in this flow regime, the shear force, the shear stress, that is the dominant force that cause the drag force, and the density effect. The density effects are minimal. So here the shear force will contribute mainly to the drag force, and here we will have a high drag force. If we look at this table 9.4 from your Munson book in chapter 9, we can see that they have derived a term for the drag coefficient with respect to Reynolds number for the creeping flow regime, where the Reynolds number is less than or equal to 1. So here we have the term for our drag coefficient, that is CD. The drag coefficient C divided by Reynolds number, that is only for the creeping flow regime. We can use this term right here, and C is related to different values that are concerned with different shapes. So if we take this shape and we place it in a creeping flow regime, then we will have the coefficient of drag, that is 20.4 divided by the Reynolds number. For a circular disc that is parallel to the flow, then we will have the value of C, that is 13.6 divided by Reynolds number, and this will be the drag coefficient, equal to a drag coefficient. And then we will have for a sphere, we will have the drag coefficient value, that is 24 over Reynolds number, and for hemisphere we will have a drag coefficient value 22.2 divided by the Reynolds number. So we have different values of drag coefficient in the creeping flow regime for different shapes, and we can read them from this table right here. To see the effect of drag force and the Reynolds number from point A, that what is actually happening, and this is actually a smooth cylinder that we are taking the points on. This is the smooth cylinder, and if you look at this diagram right here, this is corresponding to point A, and in the creeping flow regime, where the Reynolds number is very low, you can see the boundary layers. They are not separating. They are not separating at all, but they are actually adjusting to the shape of the object, and they do not separate or form any wake, and that's why the only dominant force that is acting here is the shear force. Then we move to point B right here, and the corresponding diagram to point B is this one, and here the Reynolds number is equal to almost 10. Reynolds number is almost equal to 10. This is also a low Reynolds number regime, but what happens right here is now the separation phenomena occurs. The flow will separate right here, and it will recirculate. It will recirculate. Then what will happen? This will result in a low pressure. This will result in a low pressure area or a low pressure point in the back of this cylinder, and what will happen, that this low pressure will actually suck the cylinder. It will suck the cylinder towards this side, and we will have a drag force corresponding to this point B. So this is related to this point B, where the Reynolds number is actually almost equal to 10, and you can also say that these are the stable eddies that are being generated, that These are stable eddies. These are the stable eddies. So this was point B. Then at point C, and the corresponding diagram to point C is this one, where the Reynolds number is almost equal to 100. And what happens is that in this region there is also a recirculation region, but what happens is these eddies right here are no more stable. They actually form vortices, and these vortices have a certain frequency and a certain energy, so that they travel in the downstream of this cylinder. And what actually happens is if they have energy, if they have very high energy, so they will actually exert some of that on the cylinder right back, and they will have some frequency, some recirculation flow frequency. And what will happen is that if that frequency of these circulation regions is becomes equal to the frequency of this object, then it will cause the failure of this object, because the frequency, natural frequency of this object will become the equal to the frequency of this recirculation region. So that's why failure will occur. So this is another phenomena that occurs in the Reynolds number equal to 100 regime, and the vortex formation phenomena actually occur at point C right here. Then we have point D. At point D, what you can see that the Reynolds number further drops, and the uh, Reynolds number right here is equal to, corresponding to at least 10 to the power 4. And here there is a laminar boundary layer, and we have a wide wake, and that wide wake have very unstable eddies, but they will travel and they do not form any recirculation vortices due to the high Reynolds number, because the inertial effects are now dominant in this case, as we already discussed in the previous slide, that at high Reynolds number the inertial effects will be dominant, and the shear effects will be very minimum, the viscous effects will be very minimum. So that's why the drag is actually dropping. And as we further increase this Reynolds number, so we get a dip that at point E, and that dip occurs at Reynolds number approximately equal to 10 to the power minus 10 to the power 6. That is very high Reynolds number, and this is a turbulent wake. And in turbulent wake, the length of the wake, the width of the wake, sorry, as you can see, it further reduces. So further reducing the viscous effects and increasing the inertial effects results in a reduced drag in this scenario. So this is what the effect of Reynolds number is on the drag coefficient. If we change the Reynolds number for a specific shape, then we get these different flow regimes, as we already discussed in the first. The streamlines are not disturbed, it actually flow around the object without separating. Then in the Reynolds number 10, the flow separates but into stable eddies. They get stabilized in the wake of the cylinder, but they create a low pressure region that sucks the cylinder into this region. Then at Reynolds number 100, we have unstable eddies, and these eddies actually flow in the downstream of the cylinder, and they have some energy. And if the frequency of that energy becomes equal to the natural frequency of this object, it will cause failure. And in some cases, it has in some natural occurrences, these type of studies are performed to check if the what will be the flow Reynolds number and what will be the natural frequency of the object, and if it causes failure due to the vortex generation. And this is also called the Karman vortex street wake, if we get unstable eddies and these eddies keep on traveling. But again, if we move further at the higher Reynolds number, towards the higher Reynolds number regime, then the wake becomes unstable, and the viscous effects are reduced, and the inertial effects are dominant. So we get a laminar boundary layer, but the wake is turbulent. Then at a very high Reynolds number, we get a turbulent boundary layer along with a narrow turbulent wake. So in that scenario, the drag force is certainly reduced with this dip at point E due to this turbulent wake. As we already discussed, that the inertial effects will be very high and the viscous effects will be very low, and that can be seen with this reduced width of this wake region for this high Reynolds number regime. We can also relate the Reynolds number for different shapes, that the In this graph, the character of the drag coefficient as a function of Reynolds number for objects with various degree of streamlining. That what will happen if we go from a very blunt object, that will be a plate that is perpendicular to the flow, that will be the very blunt object, and then we keep on increasing the streamlining of the object. So this, then it will convert into a cylinder, then it will be converted into a sphere, then we have an aerofoil, and then we have a completely flat plate. So what will be the effect of Reynolds number? As you can see that for flat plate the Reynolds number has no effect. For a very blunt body, Reynolds number is actually independent. In this case, the drag coefficient will remain the same. Then if we have a circle, so the circle will have a constant Reynolds number up to certain, drag coefficient up to certain Reynolds number. Then with the increasing of Reynolds number and the introduction of the turbulent regimes in the wake of the cylinder will occur, and the characteristic drag coefficient will reduce at that point. Then for the ellipse, our body is becoming more and more streamlined, then it will have a certain type of drag coefficient. And as we increase the Reynolds number, we will again have a dip due to the occurrence of the turbulent wake. So in case of aerofoil, this dip keeps on decreasing as we increase the Reynolds number. You can see that here the dip is very high, here the dip becomes low, and here the dip is actually very minimal. But why this is happening? Because due to this extension, this conical extension in the rear of this object. If you take a cylinder, then it does not actually keeps the drag coefficient low, it then again increases. But due to this conical lesion, the drag coefficient is actually kept low due to the introduction of this conical region. So we can also say that for blunt bodies, the drag coefficient value actually decreases with higher Reynolds number. As you can see, there is a sudden decrease. But for aerofoils, for streamlined bodies, the drag coefficient actually do not actually decrease that much. We can see from these dips right here. And then for flat plate, the drag coefficient actually slightly increases. So with increasing the Reynolds number. So we can safely say that for blunt bodies, if we take these bodies as our blunt bodies, then we can say that the drag coefficient actually decreases with the increase in Reynolds number. So for streamlined bodies, the drag coefficient actually increases with the increase of Reynolds number, and with the introduction of this conical lesion, we can actually reduce our drag our drag coefficient. Now let's have a look at this practical example, and you have seen that the professional bicyclists that compete in the competitions, they have a helmet like this. Look at this helmet. Look at this helmet. It has a conical lesion in the wake that will cause, if this is the flow of the air, then this will actually stabilize the wake. As we already saw in these cases, that we have some unstable wake regions as the Reynolds number increases. So to stabilize this wake region, that's why we actually extend this conical lesion in the rear of our geometry. And practically we have seen that experimental values that the drag coefficient for blunt bodies of a circle is equal to 0.5, and that for a conical lesion of this, if we add this conical lesion in the rear, then it reduces to 0.04, and that is almost equal to 92% of the drop. So you can now see that what is the effect of this conical lesion that is added right here, and you can see the actual application of such flows and such scenarios where we like to reduce the effect of the downstream wake on the drag force. So now you can clearly see the practical application, and you can also relate this to the different type of aerofoils that are used, and the Formula 1 cars that are designed as such to actually reduce the drag coefficient so they can get their required speed or the required thrust that they require for competing.